Okay, so today I'm going to continue to introduce about the quantum machine learning. So I hope you still remember our last quantum basics after this Thanksgiving break. So okay, so let's get started. So today we'll cover several points. The first is that we will use a short period of time to continue to introduce some noisy intermediate scale device. And also we'll continue to introduce a parameterized quantum circuit, and then introduce how to use those parameterized quantum circuit to do some machine learning task, and how can we train those parameters to achieve the task. And we're going to introduce the classifier, which is the basic of many different tasks, like classification tasks. And also we'll introduce how to do the noise-aware on-chip training of those quantum circuits. And finally, we're going to introduce Torch quantum library for the quantum machine learning. Okay, so the first section, I'm going to just continue our last class, where we introduced the noisy intermediate scale device. And last class, we introduced the superconducting device, which has a fixed topology. And this time, I'm going to introduce another so last year, when I introduced NISQ, actually the neutral item device is not very popular yet. But a year later, actually, they are currently the leading solution for the quantum computers, because they are the first to achieve over 1,000 qubits, right? So just a month ago, Item Computing, they announced that they have fabricated a quantum machine with 1,200 qubits, and 1,100 of them is usable. So we can see typically a neutral item device, the largest difference from the superconducting is that the items or the qubits are implemented with the nitro items. So we don't have to do any engineering on the qubit itself. So what we have to do is to do the control of the atoms. So that is the largest advantage, because you can very easily to scale to a large number of qubits, because you have almost like an infinite number of items on Earth. So you just use them to do the computation. But the difficulty is how to control them to apply the operations we introduced last time, right? So typically they are, for example, this is a large chamber, and then the items are placed here in the chamber, and then you can use the laser from the bottom and also from the front and end to control all the different states of the items. So here is a control signal that you can see. There are two different kinds of lasers. One is called a spatial light modulator, or SLM, that is basically creating a field that the items can be placed in the field to not move anywhere around. And also we have another is called a crystal optic deflector. So those ones can apply the operations to the items, and also can if you move the 2D ALD here, the items can also be moved together. So previously there are some works like in 2021 and 2022. So there are two works that trying to find how can we do computation on those fixed item arrays. So basically, you can see this array, and there are several different constraints. For example, if we are doing the operation between those two items, and then there might be some overlapping of their zone. So that will be restricting, because that will create some uncertain physics behavior. And also sometimes you cannot do all the all-to-all connections, because if the two items are too far away from each other, then you cannot apply an operation between them. And also sometimes when we do operations with neutral items, the items can lose, right? So for example, like the unwanted perturbation of the system, that will make your items just not visible anymore from the system perspective. And also besides those 2 qubit gates, a recent paper last year in ISCA also exploring how can we just elevate our control power to 3 qubits controls. So we can create those 3 qubit blocks, and then we can just use 3 qubit blocks operations to operate those gates. And the advantage of that is you can drastically shrink the duration of the circuit, because those 3 qubit gates are more expressive than those 2 qubit gates. So and also a very recent trend of using those neutral items is that actually there are additional flexibility in the topology of the items. So imagine that in the superconducting device, you just fabricate a chip, and all the qubits are lying on the chip, and they cannot move, right? And also the connections also are just fixed ones. For example, like the qubit mapping problem we introduced in last lecture. But for the neutral item array, there is a very exciting dimension of the flexibility or the freedom, which is the movement of the items, right? So we can see that this is a illustration of a recent introduced neutral item device, which is called field programmable quantum array. So that is FPQA, which is very similar to the FPGA. So maybe many of you are familiar with the field programmable gate array, which you can do the placement of the cells and also the routing of the wires according to your digital like circuit. And then actually for the quantum, that's very similar in this field programmable quantum array, where you have some of the fixed items in the whole chamber, and then you have some movable ones, right? For example, the blue ones here I mark as the blue ones are the fixed ones, and also for those yellow ones, they are movable ones. And I also put the grid here because those items can only be moved by those 2D grid, which means, for example, if you want to move those this item, you have to move the row, all the items in the row together, or all the items in the column together, right? So that creates some limitation on the flexibility, but there is also like large beneficial because benefits we can obtain from this architecture. Because, for example, if we just want to do some operation between the top left corner to the bottom right corner, we can just move the item to the nearby to this blue one and operate this very long range gates instead of doing those expensive swap gates in the fixed array, right? So, and also in terms of the control gates, there is another different from the superconducting. So imagine, remember in the last section, in the last lecture, we introduced using the microwave pulses to control each of the gates. So here, if we want to do the single qubits operations, we need to use some laser to directly illustrate the item to operate those single qubit gates. And for those multi-qubit gates, especially 2-qubit gates, the direction of the laser is different. So basically, for those 2-qubit gates, we need to illustrate the laser called Rydberg laser from the side of the whole device. So that means if you are illustrating from the side, then that means all the items are illustrated together, right? That means all of the items that is within this small distance, they are doing compulsory gates, right? So you cannot say I cannot close down this gate for any reason. For all the items within this small range, they have to do those compulsory gates. So that creates some benefits for the on one hand, we can have a very large parallelism because imagine you just illustrate once, but all the gates can be done together. But on the other hand, you also create some restrictions because say if I just want to do those 2 gates, I cannot move those these 2 yellows to the blue ones because those will introduce unwanted operations. So that give us some challenge to how to develop this compilation framework for FPQA. So here I'm going to introduce one simple technique we developed in our lab, which is called QPilot. So the basic idea is that because we have those fixed items, right? And also we have those yellow movable items. So we do a cross-stack co-design of the algorithm side and also the compiler side, which means, say, if I just want to operate this very simple circuit, like a 2-qubit gates between 0 and 1, and then between 1 and 2, and then between 0 and 2, actually, I can change the original circuit using some ancilla qubits. So the left-hand side one is directly doing operations between the original qubits. And on the right-hand side one, I can use some C0 gate to create some fan-out qubits from the original ones. And the benefit of that is you can reduce the dependency between those original gates. For example, if we just create 2 fan-outs, you can consider them as the like the decoy of the original qubits. And we create 2 decoys, like the A00 and A01. And then I can also create another decoy of the Q1 using this A10 qubits. And also using this a 2, 0 qubits, I can create a decoy of the Q2, right? So in that case, after creating those decoys, I can directly doing gates between the decoys or between the decoy and also the original qubits. And that will be exactly the same as the mathematically the same functionality to the original one. So that gave us a idea to how to do the compilation for arbitrary circuit for this. So the idea is that we just map all the original qubits in the circuit to the blue fixed ones. And if there are some gate, we can do some we can create those decoy qubits using those movable ones, right? Like using those yellow ones as the decoy qubits. And because decoy qubits can be moved freely across all the grid, right? Across all the grid, and then we can use them to route between those fixed qubits. So say if there is a gate between this blue one, like on the top right left corner and the right bottom corner, and I can create a decoy for the top left corner using this yellow movable qubits, and I can move that to the bottom right corner and apply the gates, and then we can return that. So that gives us a very flexible and also very a protocol that is very scalable because we don't have to do very complicated computations for the compilation. So here is the overall like schedule of the whole process. So basically, we have this blue array, and then we can map the algorithm qubits to those blue fixed items, and then we can create this movable AOD array like the yellow ones, and then we can perform the gates, and also according to the perform the 1 qubit gates, and according to the 2 qubit gates, we can further decide those movable, decide those the locations of those yellow qubits, and we can also move those yellow ones to perform the 2 qubit gates, and then return to the original one. Because remember that after we're applying those 2 qubit gates, we also need to recycle the ancilla qubits to make sure that the functionality is the same as the original one, right? So there is like a creation of the ancilla, perform of the 2 qubit gates, and recycle of the ancilla. So here is the animation for this whole process. So imagine we have 10 blue fixed items, right? And then we have a grid of the movable items on the top left corner, and those lines and also the column and the row lines are indicating that they have to move on this grid. So here we can see that we can move this using this gates to create ancillas, to gates and recycle, right? So this will finish one layer. And then next layer, I can also create those creating ancillas and doing 2 qubit gates and recycle those ancillas, right? We can have a look at one more, like creating those 3 ancillas and move those to perform gates, and then going back to recycle those ancillas. So in this case, we are actually have a very standard way to perform the compilation for this field programmable quantum array. So imagine if we have just 100 qubits, we can still follow the similar steps, and it is very scalable to a large number of devices. And we are the only compiler right now that is available to compile over 1,000 qubits. Okay, so just another simple example. Any questions right now? Yeah. Okay. Yeah. So another example is that we want to increase the parallelism. Remember, we introduced that another feature of our field programmable quantum array is that all of the 2 qubit gates can be executed together, right? So we just give an example of the QAOA, which is doing the max cut of the original graph, and all of the edges here are representing a gate between the qubits. For example, we have 12 qubits in total, 12 nodes in the graph in total, and then we want to find the max cut of this graph, which means like we want to cut the graph to 2 parts, and what is the max number of edges we can cross. So in that case, we want to increase the parallelism. So we introduce some dynamical programming techniques to make sure that we can, at each stage, we can maximize our number of 2 qubit gates that we can apply in parallel. So for example, in the first stage, we are checking that whether in the first row, whether we can do the gates, like if there is a gate between 0 and 1, if there is a gate between the answer is yes, so we can move this yellow one to very near to the original qubit 1. And then we are asking whether the qubit 1 there is a gate between qubit 1 and 2. The answer is no, and we continue to check whether there's a gate between 1 and 3, And the answer is yes. So we can move this qubit to here. And then we check whether if we fix those columns, and then we check other rows, whether there are other rows that we can perform gates together. And we can see that there is also an edge between node 4 and 9. So we can move this qubit 4 to near to the original qubit 9. And also we move this decoy qubit 5 to the original qubit 11. So the whole idea is that we can create a grid of the decoy, right? And then we move to the original qubits and then perform gates and return. So in this case, we can repeat this, and we can see for many stages, we are actually achieving a pretty high parallelism. Say for this third stage, we can apply all the gates between those 8 pairs of nodes just in 1 times of illustration of the laser. So that is extremely efficient and only available, possible with this like field programmable neutral atom array. Okay, so that's another very exciting device that we are currently available. Just log into the Amazon Web Service, AWS. You can see that QAOA already put their 256 machine on the AWS, and you can just play with the device. In terms of the performance, we can see compare with the previous the superconducting we introduced last lecture, and also the 2 fixed arrays we introduced in the first slides. We can see that in terms of 2-qubit gates and also the depth of the circuit, we can reduce this because we can move those very long range qubits without doing extensive swap gates. And we can also achieve pretty low average depth because of the high parallelism brought by this Rydberg laser illustrated from side. And also in terms of fidelity, because we have this smaller number of 2-qubit gates and also lower depth, we have a small 2-qubit gate error and also a small decoherent error. And overall, we can achieve around like better, around like 8% of the better fidelity compared with other baseline architectures. Okay, so that is the short introduction for the very recent device. And we can continue back to how can we use those devices to perform some machine learning task, right? So that goes to the second 2, the parameterized quantum circuit. So actually here, I want to just introduce a little bit of the big picture. So because we know that we want to apply those algorithms to different kinds of tasks, and we want to ask what is the type of algorithm, and also what is the type of the data we want to process. So there create a grid between the classical and quantum. So on one dimension, we have the classical machine learning algorithms and also quantum machine learning algorithms. And also on another dimension, we have different types of data. We have data from classical sensors. We also have data from quantum sensors. So data can be both in classical and also in quantum format. And for this CC part, like classical data, classical algorithm, we are very familiar with, because in the previous like 20 lectures, we already introduced a lot of amazing algorithms in those area. And then we also have CQ, which means classical data and quantum algorithm. So we are going to introduce this in the next several sections. And also for the QC is that we have the quantum data and also we have classical algorithm. So that is also pretty extensive, please. Yeah, so I think actually mainly for the first. So because like, for example, there's some quantum sensor from the physical environment, and then they can just connect a quantum computer to the sensor to perform the processing. But I think in the future, actually, with the development of some quantum memory, and then like the QRAM or random access QROM, and then we are able to store some information in the quantum RAM, and then after that we can directly apply some computation. So in that case, it's still quantum algorithm on quantum data, but that quantum data is from classical. Yeah. Cool. Okay, so for this for quantum data classical algorithm, because right now the quantum memory is still not very mature. So for many of the experiments, like the detection of the some like cosmic ray and also cosmic ray or detection of some physics metrics, we are still using some classical algorithm. And also, finally, we have this quantum data and the quantum algorithm. I think that is also a very bright future, because we don't have to do those very expensive conversion between the quantum and the classical domain. we can directly plug in this quantum computation operations to those quantum sensor. So there are some existing companies like I think some companies like Inflection in Denver, they try to use the quantum sensor to test the acceleration of some vehicles, and they directly detect that with the qubits, and then they directly apply the quantum operations on the qubits to perform some post-processing. So that is an example for quantum data and quantum algorithm. Okay, so for the quantum data classical data quantum algorithm, so we actually have a large number of papers and research going on. So one of the widely used algorithm is based on this parameterized quantum algorithm. So what does that mean? So parameterized here means that in the quantum device and also the quantum circuit, we have some we have some parameterized gates. For example, this rotation X gate. There is a rotation angle in this X gate. For example, we can do this arbitrary degree of rotation on the X dimension. And also we have some other gates like the fixed gate, like the CX, which is C0 we introduced before, and also some rotation gates on the other dimension like RZ or the controlled rotation X. So those different parameters give us the space that we can tune to target the specific task we want to apply. So that's very similar to the classical deep learning. So classical deep learning, you have this matrix of the weights or some different very carefully designed architecture like the attention or LSTM or some other operations. And we have parameters in those operations that we can train according to the data. We load the data and then train that using some optimization algorithm like BP or some other algorithms to make sure all the data or the parameters in the classical neural nets can perform the task we want. And that's also the high level idea here for the quantum circuit. So you may ask whether the how good is the quantum circuit to express the certain task. So here we are introducing a terminology which is called like expressivity. So we want to know like how good is the circuit covering the whole qubit space. So if the circuit can cover a large portion of the space, that means that it can have a good coverage of the whole learning space. So and also we can have a look at those two very simple examples. Like first one, we have this Hadamard gates to create some like superpositions, and then we have just a single gate rotation on the Z basis. And then we have another circuit. We have this H gate RZ, but we have another one gate which is RX, right? So and you may ask which one is better. So intuitively, the second one should be better because there is another parameter in the circuit. So how can we justify that? So we can see if we just changing the theta here and illustrate or visualize the space we can cover on the qubit block sphere, we can see that only a very small range of the range can be on the tropical here, right? So it can be covered. But if we're doing the learning task with circuit B here, we can see that many of the points on the whole space can be covered. Those blue small points are representing one example points that we can use this circuit to create. So in that case, we can see the circuit B actually have a better coverage. So and then we can see some other circuit like the identity circuit that is only covering one point. And circuit A here we just introduced can cover a ring, and circuit B we can see that it's almost covering all the places in the Hilbert space, and we can also have this most general case, which is a U case, like we introduced last time. We can see a very there are some like in non-uniform distribution of the points. You can see some of the points are very close to these points, even though we are doing the uniform sampling of the rotation angles. But on the U case, we can see a pretty uniform distribution of all the points that we can cover. So further, we can have a look at the distribution between this the single points here and also the all uniform space. So all uniform space means that you can represent arbitrary state you want to do, and then we can see for the single point the chaos divergence between the distribution that can be created by the this circuit with the arbitrary uniform distribution is very high. And then further, we can see if using this, we can achieve a 0.22 of the chaos divergence. And then all the way to using this arbitrary rotation gate, we can see the covering of the space versus the all uniform space is very close, and the chaos divergence is lower than 0.01. So that means the learning or expressivity of this gate is better than the previous ones. And also, before this expression, we also want to know, like say we have multiple qubits. What is the ability to perform the entanglement between different qubits? So just imagine that if we in a circuit we don't have any gate between the different qubits, and then we are not able to create any entanglement because you don't even do any gates between those. So how can you create an entanglement, right? So we want to use another measure, like which is Meyer-Wallich measure, to represent the entanglement capacity of the circuit, right? So that will tell us what is the capacity for that if we have multiple qubits. So there is a range of this MW measure from 0 and 1. And the 1 is for the full entangled state. And 0 means that there is no entanglement between different qubits. And we want to use this average MW to measure the entangled capacity of the circuit. So here we are just giving several examples. Say for the circuit 1 here, you can see there is no gates between different qubits. And that is no surprising that the MW measure should be 0. And then for some others, we can create that with 2-qubit gates or the controlled rotation Z gates or some other different 2-qubit gates, or whether the circuit is very deep or very shallow. So that we also have different this MW measure. So again, more examples. So we are going to show that in this graph that what is the this MW measure for those different kinds of circuit. So we can see that first of all, on the X dimension, that is the ID of the circuit. So maybe we can just have a look, one more look of the previous one. Like we have this different 19 circuit, and then this is the ID for those circuit. And then for this one here, we can see for different shape, like the circle or the rectangle here, that means we apply how many layers of the original block. And we can imagine that more blocks we have, the entanglement capacity should be better. So in that case, we can see for the circuit 1 here, all of the, no matter how many layers we apply those gates, so it's always like 0 entanglement capacity because there is no gates at all between qubits, right? And we can see that actually the circuit 9 here is actually the best in terms of the entanglement capacity. And we can see the actual structure here is that we are firstly doing some superposition, right, between those qubits using the H gate. And then using the superposition, we can create the entanglement with the CNOT gates. So in that case, we can see the circuit 9 here is pretty good in terms of the entanglement capacity. And for some others, we can see typically if we have more gates, like from more layers, from say from the right circle, just 1 layer to 2 layers, 3, we can see an increase of the entanglement capacity because we are able to apply more gates to manipulate the states. Okay, so another important aspect is the hardware efficiency of the of the circuit. So, for example, here, the parameterized quantum circuit here design need to consider the qubit connectivity, right? So, say I just have 5 qubits, and there are some gates between the 5 qubits and some connections. So maybe our design circuit should be aware of those native gates to make sure they are hardware efficient. Otherwise, we still need to insert a lot of the swap gates between those qubits to finish the target functionality. So another thing is whether those gates are native gates. So say if I want to perform some operations, so different quantum device will have different instruction set. So we want to make sure the design circuit is very suitable for the target circuit. So just like you're designing some specialized operation for your neural networks, you want to make sure it's most of the operations are like parallelizable, like using matrix modifications, so that you can accelerate on GPU. You will not do a lot of sequential operations. Otherwise, you are not able to have benefits on the specific device. That's also the case here. So for some specific quantum device, you want to design the most suitable circuit or suitable program to run on that device. Another thing is that after we design those models, which may have different architecture or structure, we still need to decide how can we upload the information from classical domain to the qubits, because we are dealing with those classical data and quantum algorithm, right? So there are several different encoding algorithms. For example, we can do basis encoding, amplitude encoding, or angle encoding, or arbitrary encoding. So those are different ways that we can encode the classical information to the qubit state. So we'll introduce all of them one by one. So the first one is called basis encoding. Basis encoding, you can imagine that, for example, in the Hilbert space, we have many different bases, like say from the all zero basis to 0001 to all one basis, right? So if we just want to represent one single number, say I want to encode the input information is just one single number, which is 2, and in binary that is 1, 0. So in that case, we can just create a quantum state that is without energy, with all the system energy on the 1, 0 state. So that is encoding this information to just one state. So for example, if I have this input as 0, and then I can use the 0, 0 as state, all the energy is on the first. And if I want to encode another number 3, and I can use the 1, 1, because the binary representation of 3 is 1, 1. So I can use this 0, 0, 0, 1 as the input state of the quantum device. However, it is very obvious that it is not efficient, right? So for just one data, we need to use maybe multiple qubits here. So, however, if we are doing multiple data encoding together, so that may create some more efficiency, because say I want to encode the information of 0 and 3 together. So say if the input here right now is simultaneously 0 and 3, or 2 channels coming in, and then I can use this entanglement between 0, 0 and 1, 1 state, creating this state, right? And we can also say encode 3 different input numbers, 0, 2, 0, 1, and 3 in this state. And then we can see, still using those 2 qubits, we can encode more information. And another thing is that, say, the basis encoding is still like very limiting, because we need to, at most, we can encode 4 information to the 4 states here, right? So in that case, maybe we can do better. So say, if I just want to encode this information on the state vector, right, instead of the basis, but the state vector of all the information here. So say I have a vector of 1, 0, 0, 0, and then I can just create the same state using 2 qubits, right? The state can be just 1, 0, 0, 0 here, the same as here. But if I want to represent the input vector in this floating number, right, like 0.8, 0.2, so I have different magnitude across this vector. So that we can also do that using these 2 qubits by encoding those input vector in the state of this 2 qubit quantum joint state, right? So you can imagine that, say, if I just have 1,000 features, 1,000 lengths of the feature vector I want to encode in a quantum machine. So in that case, I just need to use 10 qubits, because 10 qubits can bring us the state vector of 2 to the power of 10 of the length, which is 1 over 1,000. So we can just use 10 qubits to encode the information of a 1,000 over 1,000 vector. So that is the very exciting, like, large space that we can use the quantum to do. So say you have a very long documents, or you have a very large video, you want to do the processing. So that in that case, you may have several gigabytes of the information or terabytes of information. But in that case, because those quantum states can actually represent a really large space. So say if you just have all the data like created by our human in a year, right? That is around like 2 quintabytes. So in that case, we just need not less than like 70 qubits to represent all the information. So because to the power of 70, so that's exponentially larger when we have more qubits. So that is the power of the amplitude encoding. So for some other like state, for example, if you just want to represent multiple inputs together, like say I have a first first information as 1.50, another information as -2, 3, and then I can also concatenate a different information to a long vector, and then I can represent this using this state, which is 1.5 of the 0, 0, and then because the second is 0, there is no state on the 0, 1, but I have -2 on the 1, 0, and also 3 on the 1, 1 state. So in that case, there is a normalization factor at first, because we have to make sure, like all the information, the amplitude of the square of the amplitude should sum up to 1. So I can also use this circuit to represent the state to create this entanglement. So in that case, the information will be inside the state of the circuit. So imagine if we want to do some very simple matrix modification between a matrix to the vector. I just want to do matmul here, and then I can apply some operations later on this state, and that would be just directly applying those matrix to the state. So in that case, imagine that you have a 100 qubits machine, and you encode some information to the 100 qubits, and the size of the vector will be 2 to the power of 100. And when you apply some operation to the system, so the corresponding or the computation you are applying is to the power of 100 times to the power of 100 multiplications together, because you just apply changing the state of the whole vector using mathematically, that is a very gigantic size of the matrix vector multiplication. So that's where the efficiency of the operations here can be achieved over the classical operations. So another encoding can be done is called like angle encoding. So angle encoding is that we can encode the data in the rotation angles of the cubic gates. For example, we just want to encode 3 numbers like 0, pi over 2, or pi. And I can just use some gates, for example, the rotation y gates here. And the rotation angle here can be directly be the data I want to encode, right? So I can apply those 3 gates to the whole system. And then if I want to recover the information or do some computation, I just directly do the measurement of those qubits or doing some later operations. So that is the angle encoding. Another is the final one is called arbitrary encoding. So just imagine that we have this parameterized gates all across those whole circuit. So sometimes we don't have to constrain us to encoding the data at first of circuit. So even after we apply some operations, we can still doing some encoding, right? So say there are 12 different rotation angles in this circuit. There are some entangled gates between them. I can still entangle this large long vector to the whole circuit, right? Because I can just use the rotation angles to represent the state where we're trying to encode. So that is the arbitrary encoding. So in arbitrary encoding, there are many different recent works proposed, like some are proposing some entangled state to make sure that when you have distinct input vectors, the state you are creating is also distinct. So there are some recent works to trying to make sure we have better arbitrary encoding. Okay, so with this circuit architecture structure design and also with the encoding method, the next step is to train those parameters, right? Those learnable parameters in the circuit to make sure we can do some computation. So here I can just introduce, here we're going to introduce some data-driven method to do the training. So typically we have some parameters in the quantum circuit, and then we want to apply some updates for those parameters to make sure the circuit is doing some computation for the specific task, right? So this training of the parameters will be performed iteratively. For example, we have some original theta parameters, like n parameters like theta at the step n here. And then we can use those parameters to compute the specific task. For example, say you want to compute some classification task using the parameterized circuit here. And then I can also return the value or some cost function we evaluated with this parameter. So say maybe currently the cross entropy loss for the classification task, and then we can return feedback this loss to the parameters, and then we can update the parameter to make sure all the circuit or all the parameters in the circuit is doing the desired task. And then we can see that say different circuit here, maybe our task is to minimize this function, this cost function, right? And maybe that is the say for the classification task, that is the cross entropy loss. And then we want to find the way to find the minimum set of the parameter to achieve this task. And then in that case, we can further deploy the quantum circuit to perform arbitrary input. And in that case, how can we train those parameters? So this goes down to the optimization task, right? So one way to do that is very straightforward, that we can do this finite different gradients. So that means for this point, I want to know the gradients of those parameters to update. So the simple thing is that for each of the parameter, I just add a very small epsilon or minus a small epsilon, and then I can calculate the local derivative for that point for the parameter. So that is just a zero order optimization method to obtain this parameter gradients. So this advantage for this part is that it is independent for the function structure. So no matter how you design the circuit, even you are doing some hybrid quantum classical computation, you can always using this method to compute the gradients and also update your parameter. So in that case, we can see that sometimes if we have a very large epsilon, so the gradient compute will be pretty different from the actual true gradient, right? So that will create some difficulty for us to train the whole quantum circuit. So in that case, there is another thing that or another algorithm which is called parameter shift. So parameter shift rule here is the analytical method to compute the gradients for all the parameters in a quantum circuit. So in that case, we don't have to do any approximation. We just do calculate analytical gradients to make sure our update is most aligned with the landscape of the optimization. So the here we are going to introduce the steps one by one, but the basic idea is that for each parameter, we can do some positive shift, like the theta plus pi over 2, and minus negative shift, like subtract pi over 2. So you may ask, like, say the parameter shift rule is very similar to the finite difference gradients, right? Because finite difference gradient is plus epsilon or subtract epsilon. So here is pi over 2. So what's the difference? Pi over 2 seems to be pretty large, so whether that can work or not, right? So actually, this one is an analytical way to calculate gradients. So later we're going to introduce this. So for example, here I just want to obtain the gradients for the Rx theta, and then I want to compute what is the partial f theta over the partial theta here. So the first thing is that I just do the theta plus pi over 2. And then I can execute the circuit again to obtain the f theta plus pi over 2. And another thing is that I can do the subtract of pi over 2 and then compute this f theta minus pi over 2. And the final gradients of partial f theta over partial theta will be just 0.5 times this difference between those two shifts, right? So just as I mentioned, you may think that is very similar to finite difference, whether that will work. So actually, here are some like proof of that that is going to give you the analytical gradients. But the one intuition I want to mention is that maybe the proof is too complicated. But one intuition is that, say, for all the rotation gates here, say the rotation x, remember what is the representation for Ry, right? So here we can see there are some cosine and sine functions, right? So that is that when you do the partial gradient or compute the different gradients for cosine. So what is the function for that? So that is a sine function, right? So if you're doing the cosine, compute gradients of xi for cosine here, that will be the sine for that. So that's why the sine will be x plus pi over 2, right? So in that case, you can imagine for all the quantum gates with this structure, like cosine and sine structure, we can just we can use this theta plus pi over 2 to evaluate the gradient directly on that point. So that is a very simple intuition, but some more complicated proof can also tell us that the actual gradient here is represented by this parameter shift. So we can also see that the very important part of the parameter shift rule is that it gives us a way to evaluate the gradients purely on quantum device, right? So imagine that here, when we compute the gradients, I just need to execute the circuit on quantum by twice, and then the gradients will be directly using this equation to obtain. So imagine that you are training a very large circuit with 100 qubits, and then you are processing all the information of a year of the human-generated information together, and you are not able to simulate the whole circuit on a classical computer because you have no available resource to simulate 100 qubits. But you can still train the parameters using the parameter shift rule, because for each parameter here, you just need to change the circuit and then you run that twice on an available quantum machine. So there is no classical computation at all in this whole training process. So that make sure that all the things is very efficient and also very scalable to the number of qubits that we develop. So we can see that we evaluate this parameter shift rule to the on very small circuit. We just want to know whether, like in the classical deep learning, we use backpropagation, and whether that is similar here for using parameter shift. So the answer is yes. So we can see for the backpropagation all the points in the blue, and for the parameter shift, we are using a small triangulars to represent, and we can see they have a very large. They are actually exactly the same because those weight is that is giving us the analytical gradients on the actual quantum device. Okay, so here the general flow will be very similar to the training of any general task. So we are using this parameter shift rule to execute the circuit, and then maybe we have some post-processing. Say maybe I want to do some later neural nets layers to process the information from quantum, right? I can do some softmax, I can do cross entropy computation, and then there will be a loss to according to the small batch of the data we are training, and then we can do the backpropagation, compute this partial loss over partial f here, and then on the actual quantum device we want to compute the partial f over each of the theta I. So I can compute the partial f theta over partial theta I using the parameter shift rule we just introduced. And finally, because of the chain rule, what we want to obtain is the partial loss over the partial theta in the quantum circuit. And in that case, we just use the chain rule to sum from the different passes, all the passes to the same parameter here. And then because we have four qubits here, and then there will be 4 passes, and then we can sum up the gradients from 4 passes to obtain the final gradients. Okay, so for the training here, we can see here in terms of the gradients here, we can see x-axis is the number of iterations, and also for this loss function, we are using this gradient-based training to make sure our loss function is reduced and also very close to the final target. Okay, so there are some very simple training techniques like the SPSA, which means like you can simultaneously perturbate all the parameters in the circuit directly. So there is a very simple assumption, or say I have 1 million parameters in the quantum circuit, and each of them will require 1 execution of the quantum circuit, right? Twice of execution. So that will incur 2 million of executions. So maybe that is too large of the cost when we run that on the actual device. Maybe that costs several $1 million to run that on the current available machine. So how can we reduce the number of execution on real device? So we can using some better optimizers. For example, this SPSA is that we can simultaneously perturbate all the parameters in the circuit instead of changing them one by one. And then we can still using the similar to the parameter shift rule, like because our assumption is that for all the other parameters, we are using those change of the very small value will not change the whole overall landscape. Say for the original parameter shift rule, we should have a vector of all the different parameters. So for each of them, we need to evaluate this function f on the actual device. So you can imagine that the number of evaluation is the number of parameters times 2, right? But if we are using the SPSA here, we just need to evaluate the functions by twice on the actual device. And then we assume that this vector will be similar if we're changing this epsilon by a small value, right? So in that case, we can use this parameter SPSA to achieve a very efficient training of the parameters on the actual quantum device, just requiring twice of the execution to update one iteration of the parameters. Okay, so we can see for this loss function, the target is -1, and using the vanilla gradient descent, we introduced like using vanilla gradient descent, we can achieve this blue curve. And using the quantum natural gradient descent, we can have a better speed up using SPSA that is very similar to the vanilla gradient descent, but we can have a much better, much smaller number of executions. Okay. Another issue is called the barren plateau. That means when you have a large number of circuit or not a large number of qubits, sometimes you may encounter the vanishing gradient problem. So that is also the case for the quantum circuit. So say we have many qubits or many layers of circuit. A similar vanishing gradient will also make our training process very difficult. So we can see the x-axis is that the number of qubits, and y is the you can consider this as the magnitude of the gradients we can compute. So we can see when we have more qubits here, the variance of the gradients will be exponentially reduced. So in that case, when we train a very large number of qubits together, then the vanishing gradient problem will also is not negligible here. Okay, so here we can see if we just have linear depth or the constant depth, we can always see a very severe severe reduce of the gradients. So that's similar to, like, say, before ResNet, you are training a very deep neural nets, and then the gradients will also vanishing when you do the bypropagation. So there are multiple ways to reduce that, but we're going to introduce that later. So maybe we can have a short break, and we're going to come back to quantum classifiers. Okay, let's continue to the quantum classifiers. So right now we have already learned how to encode the data and also the structure of the quantum circuit, and also how to do the training for parameters. The next will be how can we put all the things together to construct the circuit to do some actual task, right? So here we can see this is a typical structure for some quantum neural networks. So first of all, if we want to do some classification task of the input image, right? The very basic learning task in your like machine learning 101 class, you must learn this MNIST task, right? So which is the handwriting digit. You have different numbers, you want to classify that. So here we can also use this example. So basically, the input image will be downsampled to a very small resolution, for example, 4x4, and then we can use an arbitrary encoder. So it's not the basic encoder or some rotation encoder. So we can create an arbitrary encoder. So that is, say, using some rotation angle encoding for this image, and we can say for each of the pixel value here, the grayscale pixel value, we can scale that to 0 to 2 pi, and then we can encode that to the theta rotation angle in those parameterized gates, right? And then later on we can apply those parameterized gates to do the training, and we can use the SPSA or some other parameters, the training techniques we introduced to train the layers in between to achieve some learning task. And finally, we want to do the measurement to project back from the quantum information to classical. So we can do this measurement on the different bases, and then we can say if we just measure on a D basis, we can obtain 4 different numbers, and after that we can apply some post-processing. Either that can be a very simple softmax directly to the classification, or you want to apply some other layers. That's fine. You can do a hybrid classical quantum computing by applying any post-processing, say, neural networks you want after this measurement. And all the process can be trained together with our previously introduced parameter shift rule to make sure the training process is scalable to the number of qubits. So here, say for the training process, we just want to classify those different images. We do the downsample from this large image to the small ones. We can still see, you can know that this is 0, this is 1. So it's still a classifier recognizable from this perspective. And then we can use these different layers, trainable layers, to perform the training according to the input data. So so that is for the classifier. So for other different tasks, for example, we want to do some drug discovery. So in the drug discovery, the most important part is to simulate the ground state energy for a given molecule, right? So that is, say, we have this molecule is CH4, and then we want to know what is the ground state energy for this. Because, say, if we want to change the distance, we want to know what is the bound distance, and then we can simulate the energy for different distance, and the stable distance will be the one with lowest energy. So in that case, we can also use several other algorithms like the variational quantum eigensolver to solve the ground state energy for this molecule. So essentially, is that we are preparing the eigenstate with smallest eigenvalue using the parameterized quantum circuit, right? So in that case, the VQE don't have any classical data as the input, right? But we need to measure the state according to the construction of the molecule. So say for this one, we have this 4 different connections between the items, and then we need to follow a specific rule to construct the Pauli decomposition for the Hamiltonian. And then we can do some weighted sum of all the measurement outcomes together to obtain the final expectation value. So our goal is that we want to minimize this value to make sure the energy is a ground state energy. So by definition, ground state should be the smallest one. So we can again update those parameters in the circuit to achieve this VQ result. So using this quantum processing units or quantum machine to doing this VQE task, that will be more efficient than classical ones because we don't have to pay the memory cost. So say if you have like 100 elements in the molecule, and then on the classical one, you need to do using some tensor word decomposition, tensor contraction method, and that can create a large memory overhead. But on a quantum, you just need to use this to do some execution forward path, and that will be very fast to evaluate. Okay, so one thing we mentioned in the NISQ era is that they have a very large noise. So you may ask, if we're directly using the quantum machine to do the training, whether that's reliable, right? So the answer for the current device is not that very reliable because of the noise we encounter on real device. So in that case, for many recent work, we try to propose something called noise-aware training, right? So just like for the training of the classical neural nets, you want to make sure sometimes aware of the adversarial attack, right? So in that case, that's similar here. But the attack here is the attack you can consider as an intrinsic one. It's not from some malicious third party, but for the quantum device itself, they have some noise. So we need to do some noise-aware training. So we can see here the impact of noise on the gradients is pretty severe. So say for this classical training and classical test of some quantum circuit purely on classical simulator, we can see the accuracy here is the classification accuracy. And we can see in the blue here, when we have like several thousands of the training steps, we can have a steady improve of the accuracy. But on the quantum device, if we are doing the parameter shift rule we just introduced in the third section, we can see the training process is also increasing, but not very stable. And also with the same number of training steps, there is still a large gap between the noise-free versus the noiseless performance, right? So our goal is how to close this gap with some noise-aware training to make sure the result is very stable and also very reliable when we run that on the actual large device, right? So here we can see a very interesting phenomena is that, say, during the training process, we use the parameter shift to calculate gradients. So the gradients can be large, can be small. If its gradient is very small, we can see the relative error is very large. So that is intuitive because, say, the noise is always have a fixed magnitude, and if you have a large gradient, so maybe the overall like percentage of the noise in the large gradient will be very small. But if you have a small gradient, and then maybe that is just completely changed by the noise. So you can see when the gradient magnitude is small, the relative error is also very small. So we can see, but if the magnitude is very large, we can see a trend of the decreasing of the impact from the noise. So that gives us an idea that we can actually do some pruning of those gradients. Say if the gradient's magnitude is very small and very unreliable, why won't we use that to the train the quantum circuit? We just freeze those parameters with regard to those gradients, and we just train the remaining ones, right? So that is in that case we can avoid those very unreliable gradients and only use the reliable gradients to update our parameters. So here we can see another example, not only for the San Diego machine or the Casablanca machine. Yeah, a very interesting thing is that the IBM machine, they are always named by some places. And when I first used those machines, I thought, oh, IBM is placing their physical machine all around the world. Actually, they are just naming that. All of them are together in the IBM's like New York office. It's not anywhere else. But I think the beginning of this year, they have a breakthrough that they put some physical device in the Cleveland clinic and in the hospital, right, in Cleveland, and they are placing the machine in the restaurant, like in dining area, so that everyone can have a look at that. So that's a very cool and very large machine. Okay, so back to our experiments, we can see for the Casablanca machine and the San Diego machine, and also among other machines, we can see a steady trend of the more reliable performance when we have a larger gradients. So the idea will be whether we can find some way to find those small gradients parameters, and then we can freeze those parameters when we do the training. And one step further, if we can predict several steps, say for next several steps, the gradient will be small, and then maybe we don't have to do the computation of them at all. So that will not only increase the reliability because we don't use those unreliable ones, and also increase the efficiency because we don't compute those unreliable gradients at all. So in that case, we are doing this probabilistic gradient pruning. So the idea is that before pruning, we have all the parameters, and then in one step of the training, we can just doing the calculation of those parameters with that can give us large gradients, because large gradients will be more reliable. And then we use those large gradients to train to update the parameters. And for the others, we just freeze them. So say, but because we want to do this like speculative for those unreliable ones, so here we are proposing a way to do those speculation, which means we can have some accumulation of the gradients. So say if the gradient is very small for multiple steps, and then because landscape is not changing very drastically, so we can predict that in the next several steps, the gradients may be still pretty small according to our empirical study. So we are using this accumulation window, which we accumulate the gradients. And then after we accumulate that, we can do some sorting. So if the gradients are very small, then in the next several steps in the pruning window, we will just freeze those small gradients parameters. And then we can, after several steps of the pruning window, we return to those accumulation window, because after those several steps, the landscape may slightly changed, and we need to update this parameter accumulation again. So here we keep a record of the accumulated gradient magnitude. So say in the accumulation window, we do one step, another step to accumulate the magnitude, and the third step to accumulate its magnitude. And then during the pruning window, according to this magnitude of the theta all the way to theta 4, we can decide which gate we want to do the pruning. So say maybe for this theta 2 and theta 4, they have small value, so we just freeze them and then only update the theta 1 and theta 3. So in that case, we first of all don't have to rely on those unreliable gradients on theta 2 and 4, and also we don't have to pay the cost at all for the calculation of the theta 2 and theta 4 gradients. So we can see using our probabilistic gradient pruning, we can achieve a better performance compared with the pure like quantum training by around 10% of the classification accuracy. And also in terms of we sometimes can even have better accuracy than the classical train on a simulator, because we can adapt to the actual noise on the device, because the gradient is still aware of the actual device noise. So say here we can see the performance for the in the classical train and also QC train performance. We can see in the right curve here, we can achieve a better accuracy on this actual IBM 2 San Diego machine. Okay, so another thing is that we can compare this the loss against the classical training and also the QC training. So the classical training is purely noise-free. So we can imagine the loss should be the best. And then if we train on a quantum device, the loss is worse because of the noise. But with this gradient pruning, we can achieve better lowered loss because we close this gap a little bit. And we hope that we can further develop some other techniques to further close the gap between the noise-free one and also noisy one. Okay, so in terms of the scalability, we can see our on-chip training is very scalable because all of the computation doesn't require any classical simulation. So classical simulation, remember, is exponentially costly. And then for the number of qubits, we can see if we're doing a classical one, we can see a pretty very steep of the increase of the cost in terms of runtime and also memory cost when we have more than 30 qubits, right? And if we're doing quantum, the cost is linear. Like say for the memory here, just the number of quantum register, right? So it's increased linearly, and also in terms of runtime, because we are still applying the operations linear to the qubits, so it's still linear. So we can achieve a much better scalability with this on-chip training method. Okay, so again, for this probabilistic gradient pruning, we can compare with the deterministic one. We can still have around like 3% or to 7% of the increasement of the accuracy. Yeah. Okay, so finally, I'm use several minutes to introduce a little bit about our infrastructure, which is Torch Quantum. So Torch Quantum is a library and also programming language we are developing with the PyTorch interface and also all the PyTorch design principles in mind. So we believe that a good infrastructure is very critical to explore this quantum machine learning space, like how we can construct arbitrary encoding, how can we construct the circuit to learn, to train, and also what kind of pruning techniques, quantization techniques, and also what kind of training optimizer we want to use. So in that case, we are developing the TQ towards quantum, and all of the operations are implemented in the basis PyTorch operation and also data structure. So in that case, all the quantum gates can be simulated on GPU, and accelerated by GPU. And we have a very fast speed, and also all the PyTorch supported gradient based optimizers can be used off the shelf. And also we have some common intermediate representation. So we are, say, if you want to construct a circuit in PyTorch using Torch Quantum, and then later on you want to execute that on the actual quantum device, and we provide a push the button pipeline. So you just need to call some function in TQ, and that can automatically construct a circuit that can be directly run on the IBM device. So we also have some like noise aware training techniques and integrated to the TQ device, and that is we also have several model tool in the TQ that you can use directly. So TQ is also like used by several research institute. For example, some institute from Purdue or from UCSD, they are using our library to construct their own model. So I think around 50 papers already been published using the TQ library. Okay, so some features, we have the GPU accelerated processing. We have a very wide range of support, whether it's a state vector simulation or density matrix simulation. And also because we have this dynamic graph. So just imagine many of you are maybe familiar with the difference between TensorFlow and the PyTorch, TensorFlow 1 versus PyTorch. And they have this static graph. And that's also the case for many other quantum libraries. Many of the quantum libraries, they are using static graph, which means you construct the circuit and then do the compilation and then running. But in the TQ, you can do this dynamic computation graph. So after applying operation, you can directly check what is the current state of the system. So that gives us a large convenience when we want to do the debug for the system. And also we have support for different levels. Remember that we introduced the gate level and also the pulse level. On the pulse level, we need to solve some Schrödinger equation, the Limlard master equations. We also support that support the GPU accelerated PD solver, so we can also the gradient based process, so we can learn how can we do the computation on the pulse level. Again, some converters to some other frameworks. So it's overall, we want to create this very good and convenient tool to enable those machine learning community people to also do the quantum machine learning research. So here are just simple example as we introduce the quantum neural nets, right? So here, basically using the TQ, we can import the torch quantum as TQ and torch quantum dot functional as TQF, and also the construction of the model is very similar to the construction of classical neural networks. So in classical neural nets, we have the init function. So the QFC model here is also a child class for the n dot module, and then we can specify the quantum device we want to use. For example, the TQ dot quantum device, and we can specify how many qubits we want to use. And then we also have the measurement. So we need to specify what basis we want to measure the result. And later we can specify the encoding. So say I want to use this, remember in the classifier, we have the rotation gates to do the encoding. So we can specify the encoder gates. Later we can specify some trainable gates, like whether it's rotation X or the CRX case. Together, we already instantiate those gates. And for the forward function, we are still calling a forward in the TQ. So in the forward function, we have the input X as the image. We can do some downsampling and reset the quantum state to our zero state. And then we can apply those entangled operations to entangle those image to the quantum state. And then we can do those trainable gates later. And also we can apply some other non-trainable gates. Imagine in the classical domain, you want to apply some ReLU gates or some softmax. Those gates are not parameterized gates. So we also support those ones like Hadamard gates, the CNOT gates, or the arbitrary unitary gates you want to define by yourself. And finally, we can perform some measurement, right? Measurement directly using this measure class, and then return this X. And finally, here, this is a pure torch tensor, right? And then you can apply any of the other layers you want. Say you want to apply a transformer, that's fine. You can apply a transformer here. Or you want to apply some other gates like softmax, that's also doable. So finally, we can return this information, which is the classification result. Okay, so that's our today's lecture. We introduced the neutral atom quantum device, which is a very popular and recent device for the for the NIST computations, and also very scalable. And we introduced the PQC, the construction of the circuit, the encoder, how to do the training, and how to do the noise-aware training. And finally, we introduced the TQ library for the QML. Okay, so I hope you enjoy this QML lecture. And next step, we're going to introduce more techniques, especially how can we construct a good circuit architecture or good circuit structure to learn in the next lecture. So, okay, that's all for today. Thank you, and any questions?